In this video, we're going to go over hypothesis testing. We are going to look at the chi-squared distribution, and in particular, we're going to look at the goodness of fit test. The chi-squared distribution has a couple different tests, so we'll look at the homogeneous test in a later video. Okay, so the reason that we need another test is because in Chapter 10, you were only looking at two populations. So you were looking at mainly the proportion of one population equaling the proportion of the other, and then all of those alternative hypotheses. So if we have more than two, we need a way to test that all at once, so we're not testing all those pairs. So an example of this is you want to test the claim that a die is fair. So we all know that a die has 6 sides, and if the die was fair, that means that the probability of rolling a 1 should be equal to the probability of rolling a 2, which also should be equal to the probability of rolling a 3 and a 4 and a 5 and a 6. So each roll should have a probability of 1 out of 6. So we would make that notation of P1 equals P2 equals P3 all the way up to P6, and then that would be 1 out of 6. And what that means is each one of these probabilities is the same, and it's 1 out of 6. So again, that's what our goodness of fit test is going to do. How well does our distribution fit with what we expect to happen? And on a fair day, we expect each face to be rolled about 1 out of 6 times. In order to do that, we would have to do an experiment. So if we want to test that claim, we have to compare the actual number of observations in our experiment in each one of the categories, like rolling a 1, rolling a 2, etc. And then we compare that to the number of observations we would expect. So we know the probability of what we would expect. So depending on our number of trials, we could get the expected number of 1s, expected number of 2s, etc. For example, if we were to roll the die 600 times, and each time we wanted 1 out of 6, then each one of these would be 100 that we would expect to roll. Okay, so here's our definition. A goodness of fit test is an inferential procedure to determine whether a frequency follows a claimed distribution. And again, this works for multiple outcomes. This is what we have for our chi-squared distribution. So we have our notation here. It looks like a little curly X, but it's actually a Greek letter, chi. Chi-squared is not symmetrical, so it's going to be skewed. The shape and the skewness of the graph actually depends on the degrees of freedom. We do know that as the degrees of freedom increase, remember degrees of freedom are sample size minus 1, so that means if our sample size is increasing, the distribution becomes more symmetrical. And just like all of our other values when we're doing our z-test or t-value test, the values of chi-squared are non-negative, so everything is going to be above that x-axis. We will be doing the same type of testing, just a different function in our calculator. But know that we're still finding that p-value, which is really the area under the curve. Okay, so this is what we need for our goodness of fit test. First thing is we need expected counts, so that's denoted by E sub I. The little subscript here, this I, just stands for the multiple observations we should have. So for our die, that would be a 1, a 2, a 3, all the way up to 6. So that notation is not so important, just this formula. If we want an expected count, we have to take n, which is our sample size, and multiply it to the probability of that event actually occurring. Second, we need observed counts or observed values. These are labeled O. These will be given, so these are from our experiment. Third, we need to make sure our conditions are satisfied. So in order to do that, remember that for means, we looked at our sample size being greater than or equal to 30. For our proportions, we checked that n times p times 1 minus p was greater than or equal to 10. So for our chi-squared test, we just want to make sure that all expected counts are greater than or equal to 5. So it's the only thing we have to test and make sure that the condition is met for this one. Number 4, we have our test statistics. So this one's going to be a little bit different than our Z or T. You know that the Z and T are pretty similar, So this is our brand new formula here. Remember, this capital sigma means sum, so we're going to add up all of the observed values minus expected values squared divided by the expected values. Degrees of freedom here are the number of observations minus 1. So on our die, we had 6 different possible outcomes, so 6 minus 1 would give us a degrees of freedom of 5. Once we have our test statistic, we're going to get our p-value. And to do that, there's a couple different ways depending on the calculator that you have. You can enter the observations into L1 and expected counts into L2, so that will be the same for everybody. And then if your calculator has the test, the goodness of fit, so GOF test, we're going to use that. If not, I'll show you how to go through and use your list to help you. So you're going to still enter your observations into L1, your expected counts into L2, and then we're going to use L3 to help calculate this entire formula right before we add it up. And then we'll use our chi-squared CDF distribution, and that comes from our second vars, which we've used before. So I'll show you both types of ways, just in case your calculator doesn't have one of the functions. Okay, so just remembering our steps in hypothesis testing, we're going to determine the null in alternative hypotheses. We will select a level of significance, find the test statistic, determine the p-value, make a decision, and then finally state a conclusion. Okay, so let's look at an example. Teachers want to know which night each week their students are doing most of their homework. Most teachers think that the students do homework equally throughout the week. Suppose a random sample of 56 students were asked on which night of the week they did the most homework. The results are in the table below. So we can see the number of students, and on Sunday, 11 students did most of their homework. On Monday, we had 8 students, and so on. So looking at this distribution, it looks like Sunday night is pretty heavy, and so is Tuesday and Thursday. So maybe Sunday, people are getting ready for school on Monday, so they're going to do a lot of their homework. Same thing on Thursday. Students don't want to do a lot of homework Friday, so maybe they just do it Thursday instead. So we want to see, is it really equal statistically, or are these numbers vastly different? Okay, so following our steps in hypothesis testing, step 1, determine the null in alternative hypotheses. So teachers think that students do their homework equally throughout the week. So what we're looking at is the probability that you do your homework Sunday is the same as Monday, is the same as Tuesday, so on and so forth. And because we have 7 days of the week, each one of those probabilities will be 1 out of 7. So I put a little blurb here that all days are equally likely. And it just means that you're equally likely to do your homework on Monday, Tuesday, Wednesday, all the way to Sunday. For the alternative hypothesis, we're not going to actually write that in notation, so we're going to say at least one of these days does not follow this equal distribution. So it wouldn't matter which day, it just wouldn't be 1 over 7. So our null and alternative hypotheses are slightly different than what we've been writing before. So we're going to write that alternative in words instead of notation. Okay, so here's that example again, just in case we need those numbers. So step 2, we're going to select a level of significance. Doesn't look like they gave it to us, so we can use any reasonable alpha, 0.05, 0.1. 0.01 would be a little bit extreme just because it's doing homework, and that would be a 1% significance level, so we'll just go with 0.05. That's reasonable. Step 3, we're going to find the test statistic. So let me go ahead and put that formula up here again. So remember that the test statistic is the observed values minus the expected values. We're going to square that, divide by the expected values, and then the last thing we're going to do is add it up. So we have the observed values. These up here, this 11, 8, 10, 7, 10, 5, and 5, those are all of our observed values. So we need the expected values. So let me go ahead and put that part up here. The way that I got this, remember expected value is n times p. P P being the probability of each event occurring. So if I add up all of these students, and they actually give us the total up in the problem, this 56, if each day was equally likely, then I'd take this total number and divide by 7, since there's 7 days of the week. So 56 divided by 7 is 8, and because they're equally likely, we would expect about 8 students to do most of their homework per day. Okay, so how does that work in the calculator? So in order to get the test statistic, we're going to go Stat, Edit, and we're going to enter all of these observed values, so this first row right here, into L1. So let's do that. Okay, so we have all of our observed values in L1. Let me go ahead and put the expected values, or the expected counts, into L2. And this one's a little bit easier just because they're all 8. So we just need to put in 8 7 times. Okay, so a couple different ways we can do this goodness of fit test. So let me quit out of our list and let me show you both ways. So if we go to Stat, Test, we're looking for a GOF. So some calculators have it and some don't. So if it does have it, definitely want to use it. It's usually, oh, there it is. It's way down at the bottom. So mine is letter D, and it says chi-square GOF test. So that's what we want. And then we just make sure that all of our lists are correct, so make sure you change this each time. You're always going to put those observed values in L1 and expected counts into L2, so that should remain the same unless you're using multiple lists for different problems. Degrees of freedom are 6. Remember, that's n minus 1, so if I count how many observations, how many days of the week, I have 7. Minus 1 is 6, so I'm going to keep that, but if it were different, just change it to 6, and then I'll press calculate. So here I get my 4.5 chi-squared. So let me go ahead and put that there. And then remember, this also gives you that p-value, so we need to hang on to that for later. The other thing that it gives you is some information down here. And really what this is just telling you is how much each day contributes to that chi-squared value. Okay, so let me show you how to do this if you don't have that goodness of fit test. So if I go into my distribution, actually first I have to go alter that list. So I'm going to use L3, and I'm going to follow this formula here except for the sum. So I've got my observed values minus expected values, square it over expected values. So I'm going to go all the way up to L3 here, and I'm going to put in parentheses, just following my formula right after the E. Now observed values are in L1, so I'm going to go second L1 minus second L2, close parentheses, put a squared. Again, notice I'm just following my formula, and then divided by, and the expected counts were in L2, so I'll put divided by L2, and then press enter, and it's going to fill in that list for you. So the last thing we need to do is this big capital sigma up here, which just means sum. So I'm going to quit out of this. I'm going to go to Stat, Calc, one variable stats, and I'm going to add up list 3, so I want to only look at list 3. Let me arrow down through frequency and just do calculate. Okay, so we don't need the X bar. What I'm really looking at is the sum right here. So the sum of that list is 4.5. So notice that it matches over here. Okay, so we've got our chi-squared test statistic. So let's go ahead and go on. We need to determine the p-value. So let me revisit again. Let me clear this out. Stat, test, and I'm just going to go grab that goodness of fit test again. So we still have observed values in L1. We still have expected counts in L2. Degrees of freedom are still 6 because we didn't change anything. So let me just recalculate that. And we got a p-value of 0.6093. Okay, so I'll write that down. Again, if your calculator does not have a goodness of fit test, let me show you how to do that. So we're going to go to second vars, and we're looking for a chi-square CDF. And it looks like mine is number 8. Okay, so the lower bound and upper bound degrees of freedom, those are all things that we need to enter. So let me remind you just that notation on that other slide. If we're using the chi-squared CDF, our lower bound is going to be our test statistic, which is 4.5. Our upper bound, because we want to sum basically to infinity, so we're going to put 1E99, that's our scientific notation that we can enter into our calculator because we don't really have an infinity button on our calculator. And then degrees of freedom are 6. So I'm going to go ahead and enter that. So 4.5 for my lower. 1. Now the E is actually second in that little comma. It says EE on your calculator, but it actually just shows up as E. So 1E99, that's our infinity. Degrees of freedom, 6. And then paste, and all we have to do is press enter, and notice that we get that same p-value. So again, depending on what functions your calculator has, you can use one or the other. If your calculator has that GOF test, you don't have to do both, just do one. I just wanted to show you how to do both. Okay, so notice that these are the same, so that's your p-value. Next, we need to make a decision, so that's where we ask the same question every single time. Is the p-value less than alpha? So our p-value was 0.6093, and we chose an alpha of 0.05. And this inequality is no, 0.6093 is not less than 0.05, so we do not reject the null. And then finally, our last step, state the conclusion. If we do not reject the null, then we say there is not sufficient evidence to support the claim, and I've rewritten our null and alternative just so we knew what the claim was. So the claim was at least one of the days does not follow that equal distribution. So our conclusion would read there is not sufficient evidence to support the claim that at least one of these days does not follow an equal distribution.